Hello everybody, Dr. Jenkins here. So we're gonna get right back into respiratory. We still have quite a bit to cover, so I'm gonna move pretty quickly. But as usual, I'm gonna make sure that I point out what is most important. So we ended off in lecture going through the respiratory tract, right? You know, I keep doing this over and over again. Make sure you're able to go through all the structures of the respiratory tract. Nose, nasopharynx, oropharynx, laryngopharynx, larynx, trachea, primary bronchi, secondary bronchi, tertiary bronchi, and so forth. We talked about ventilation, the process of how we inhale and how we exhale, that we utilize the principles of volume and pressure being inversely related. So when we inhale, we contract muscles to increase our lung volume, and when lung volume goes up, the pressure goes down. Whenever the pressure in your lungs drops below the pressure in the atmosphere, air is going to move from higher pressure in the atmosphere into lower pressure in your lungs. And then we talked about exhalation. The opposite is true. Make sure you review all of that, as well as what muscles are being used for each during breathing at rest, and then also forceful breathing. So we have a couple odds and ends to get through. So we're going to kind of pick up where we left off, and these are just odds and ends, but they're important. Make sure you can define anatomical dead space and physiological dead space. So, anatomical dead space. This just refers to the fact that there's a volume of air that doesn't make it all the way down to the alveoli. If we breathe in about 500 mils of air, that's what tidal volume is, about 500 mils per minute. If you breathe in about 500 mils, and then that 500 mils of air begins its journey down the respiratory tract, only about 350 mils make it to the alveoli. And this is because some of that air is trapped or filtered out by the cilia. So there's a volume of air that stays in the conducting tube. You don't have to know the amount. I just did that as an example. But it's an important principle. Not all the air we breathe in makes its way down to the alveoli. Some of it gets trapped along the way. And the volume of air that gets trapped along the way is called anatomical dead space. The volume of air that gets trapped along the way is called anatomical dead space. It's by design. Then we have physiological dead space. And I apologize for these arrows. This blue arrow, I don't know why it's there. Whenever I bring it over from my laptop, it makes that weird thing. So then there's a physiological dead space. We don't exchange all of our air into the blood. So the physiological dead space is a certain volume of air that reaches the alveoli, but isn't exchanged. Another word for perfused is exchanged. Physiological dead space, the volume of air that gets to the alveoli, but isn't exchanged. The volume of air that actually makes it to the alveoli, but isn't exchanged into the blood. We don't exchange all of it. And this is by design. It means that if we all of a sudden, in a moment's notice, need to exchange more air, maybe we're beginning to exercise. If we all of a sudden need more air, we can go back to this little physiological dead space, this air that is there in the alveoli, but usually isn't exchanged. I know it's a weird way of saying it, dead space. It's not really dead, it's just a way that they refer to it. Okay. Be able to define anatomical dead space and physiological dead space. Okay. So now we're getting down to our next big functions. So remember, I'm trying to present these in order. We talked about ventilation. Ventilation is the process of bringing air in. Well, after we bring air in and it makes its way all the way down through the respiratory tract, we have our first gas exchange. And this is called external or alveolar. So we're going to use interchangeably external or alveolar gas exchange. This is gas exchange between the alveoli and the blood, or the lungs and the blood. We bring air in, it makes its way all the way down to the alveoli, and here we have our first gas exchange. Gas exchange between the lungs, alveoli, and the blood. How is oxygen going to move? Well, oxygen is going to move from the lungs. O is oxygen. Oxygen is going to move from the lungs into the surrounding bloodstream. That's the whole point. We bring in this air, it makes its way down to the alveoli. We want to actually exchange the oxygen from the lungs into the blood. At the same time, we have carbon dioxide in the blood that moves from the blood back into the lungs. I don't know why people commonly miss this. So, whatever you have to do, but I'm trying to be as straightforward as possible. External or alveolar respiration. Gas exchange between the lungs and the blood. External or alveolar gas exchange between the lungs and the blood. Know which is moving in which direction. Oxygen is moving from the lungs into the blood. CO2 is moving from the blood back into the lungs. Memorization, folks. You can do it. Okay. A couple of points here. As usual, there's more on these slides and you need to know, so I don't want you to freak out, okay? I'm going to point out the points that you need to know. These gases must dissolve in water before they diffuse. Oh, excuse me. So didn't we just say that our first gas exchange is alveolar? Gas exchange between the alveoli of the lungs, really bad drawing, but you're used to that by now, and the surrounding bloodstream. So we talked about how gases move. Oxygen is going to diffuse from the alveoli into the blood. But now we're adding something. That oxygen has to dissolve in water before it can diffuse through the membrane. So let me just go back. What that means is, let me just put a little bit of blue. Remember, there's a layer of fluid surrounding the alveolar membrane. It's called surfactant, produced by the type 2 cells. So what we're saying is oxygen has to diffuse into that fluid first. Dissolve is a better word. Oxygen must dissolve in that fluid first, and only then can it move into the blood. So yes, in external or alveolar gas exchange, oxygen moves from the lungs into the blood. Now I'm just adding a step. In that process, oxygen must first dissolve in water before it diffuses. You don't need to know Henry's law that's related to this. Right now, all you need to know is this fact. Here in the lungs, the gases must dissolve in water before they diffuse. Simple, simple, simple. Okay. I've tried to add pictures. People get this confused, so whatever you need to do, try and keep it simple. External or alveolar gas exchange between the alveoli and the blood, lungs and the blood. How does oxygen move? Oxygen is moving from the lungs into the blood. How is CO2 moving? CO2 is moving from the blood back into the lungs. Now, I did do this drawing as a review, but also to show you some other things. When we compare, let me just go ahead for a moment. When we compare the concentration gradient, what we're going to see, oxygen always has a greater concentration gradient. The gradient is always going to be higher in oxygen. You need to know that. Let me go back for a moment. The concentration gradient is higher for oxygen. Look at these numbers. You don't have to know these numbers, but they're there just to make a point. Here's the side of oxygen. On this side of the membrane, it's 100 millimeters of mercury. On this side, it's 40. That's a big concentration gradient from 100 to 40. That's oxygen. Now look at CO2. CO2 is going from 45 millimeters of mercury to only 40. So isn't that a much smaller gradient, 45 to 40? It's still a gradient, but it's much smaller. So comparing the two, oxygen always has a bigger concentration gradient. How then does carbon dioxide keep up? Because it is more soluble. So both gases have a concentration gradient. Both gases are soluble in water. We know that both gases have to dissolve in water before they diffuse across a membrane. Both gases have a concentration gradient. Otherwise, how would it be able to go from high to low? There's both. However, oxygen is more reliant on its concentration gradient. Which gas has a higher concentration gradient? Oxygen. The next point, which gas is more soluble? CO2. So carbon dioxide is more soluble in water. Oxygen has a greater concentration gradient. When put together, they even out. This is how they can both keep up. Carbon dioxide is more reliant on the fact that it's more easily soluble in water. Oxygen is more reliant on its concentration gradient. All right. Okay. You do not need to know about ventilation and perfusion coupling. I might need to revisit that. I know you're snickering at home. You don't like me saying this. I do try and think about what is most important for you to know. Okay. You don't need to know these bottom things. That I can say for sure. But there is a point that I think is really important for us to know because it really matters during exercise. Your lungs have the ability to direct airflow to and away from areas of lungs based on need. Your lungs have the ability to direct airflow to and from areas based on need. I'm going to attempt a bad drawing. I know I'm getting into dangerous territory here. Let's see. All right. Trachea comes down. Let me do black. I want to do black here. Trachea comes down. Then we have the bronchi. And surrounding them all would be the lungs, right? Let me do lungs in blue, just to make it pretty. So here's one lung. Here's another lung. It's really bad. If nothing else, folks, you can have a good laugh at my expense. I'm okay with that. Okay. Oh, it's so bad. So here's what I want to point out, though. Inside your lungs, we have different zones. You don't have to know this. If you were to take a more advanced exercise physiology class, you would be able to divide the lungs into zones, into areas. You don't need to know that. But what I want to point out is we can direct airflow to and from areas based on need. So let's say that on what we're viewing to our left is what's happening at rest. And then we're going to compare it to what's happening during exercise. At rest, when we bring air in, we're only going to exchange gases here. Let's just say that we're going to exchange gases in those 3 zones. There's going to be a lot of physiological dead space. Remember, there's a dead space where we don't exchange. So at rest, we're only utilizing, let's say, 3 zones. That's it. All this other part is not being used. Your lungs are very efficient. So how that works is we do this by constricting and dilating. We constrict and we dilate. So in this example, we dilate to these 3 areas, dilate, 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 but then all the other airflow, we constrict the vessels. So blood is not going. Blood is not going to these zones. We constrict those vessels. Blood is not going. We dilate to open up air, open up the bronchioles to certain areas, but then we constrict the others. However, when we exercise, don't we need to bring in more air? And instead of only using 3, now we're going to use more. So now, instead of using just 3 zones, we're using 1, 2, 3, 4, 5, 6, 7. And we do that, of course, by dilating more of these. So instead of constricting to some, we're pretty much dilating to all. And that leaves less space that we're not being used. I know that this might seem unnecessary for me to draw out, but the extent to which this happens is quite significant. At rest, we are only using a small section of our lungs. At rest, we're only using a relatively small section of lungs. We don't want to waste energy, and we don't need as much gas exchange because we're at rest. What that means is during exercise, we have the ability to open up way more areas of the lungs. And we accomplish this, of course, through vasoconstriction. If we don't want air to go to a certain area of the lungs, we constrict. When we do want airflow to move through a certain area of the lungs, we vasodilate. That's what this is talking about. You don't need to necessarily know it as ventilation perfusion coupling, but just the idea. Okay, so I'm trying to present this in order. So we bring in and out air through ventilation. We already talked about our first gas exchange, external or alveolar gas exchange between the lungs and the blood. Well, if we were following oxygen, we brought in oxygen. During external or alveolar gas exchange, we exchanged oxygen between the lungs and the blood, and now we have oxygen in the blood. So a quick review of how we transport these gases in the blood. You already know how we transport oxygen. Let me go with, I kind of like green. Most of our oxygen is transported as part of hemoglobin on the red blood cell surface. That should be a review for oxygen. What about carbon dioxide? This should also be a review. Carbon dioxide is transported through bicarbonate. Most of CO2 is transported through bicarbonate. That is a review. We already saw this. I'm just saying it again. You don't need to know all the details. Do you remember, though? Let's talk about CO2, carbon dioxide. We have CO2 building up in the tissues. But remember, CO2 cannot be transported by itself in the bloodstream. So we kind of take that CO2 and we go through a series of chemical reactions and we roll up CO2 as part of the bicarbonate ion. We can't have CO2 in the bloodstream by itself. It turns it acidic. So we purposely move this equation to the right to wrap up CO2 as part of bicarbonate. And that's how it travels in the bloodstream, as part of bicarbonate. But then, once we get to the lungs, we have to reverse it. We take that bicarbonate, and now we break it back down to reform that free CO2, only in the lungs, so we can breathe it out. I'm not going to ask you to write this equation down, but the principle is very important. Okay. Now we're going to get to our second and final gas exchange, which is internal or systemic gas exchange. Remember, people get this confused. Just memorize the definitions. Now we're talking about systemic or internal. We can use these interchangeably. Our first gas exchange was called external or alveolar. Our first gas exchange was external or alveolar. Our second gas exchange is internal or systemic. This is gas exchange between the blood and the tissues. This is gas exchange between the blood and the tissues. So now this oxygen is moving to its final destination. Oxygen will move from the blood into the tissues. At the same time, CO2 that has built up in the tissues will move from the tissues back into the blood to be taken back to the heart and then to the lungs to be breathed out. Internal or systemic gas exchange. Gas exchange between the blood and the tissues. This was the whole point of breathing to begin with. Think about oxygen. We breathed air in, and then we filtered it. The oxygen that made its way to the alveoli, we exchanged oxygen from the alveoli into the blood. Then we transported that oxygen-rich blood to the heart, and then it was pumped out to the whole body. And now we are actually delivering oxygen to the tissues. This is the whole point. It's like your Amazon package. What good is it if it's never delivered? As you look through these PowerPoints, and I apologize for all these arrows, you might see this terminology, loads or unloads. I am not going to use those because I find them to be confusing. I prefer to talk about how things are moving from where to where. For example, internal or systemic gas exchange between the blood and the tissues. How is oxygen moving? Oxygen moves from the blood into the tissues. CO2 moves from the tissues back into the blood. That's how I prefer to talk about it, not loads or unloads. Now, same thing. Which has a higher pressure gradient? Oxygen. How does CO2 keep up? It's more soluble. You don't need to know those numbers. It was just making a point. All right, folks. I'm going to end this video because, as you saw, I need to charge the battery for the Apple Pencil. And also, I want to give you a moment to digest what we just talked about before we finish this chapter out. All right, I'll see you for the next one.